Nobody likes quantum mechanics. I'm serious, nobody likes it. Quantum mechanics is confusing. Quantum mechanics is weird. Quantum mechanics is non-intuitive. Quantum mechanics just doesn't make sense. And this is a fact that we have been struggling with for over 100 years, basically ever since we invented quantum mechanics in the first place. And part of this confusion is based on reality, which is that quantum mechanics as a description of nature is very non-intuitive and doesn't link up with our normal sense of how the world operates. And part of it is due to how quantum mechanics is taught, because even physicists are taught quantum mechanics in a very confusing nature. I remember when I was an undergraduate student in physics, we learned some basics of quantum mechanics, some things about like wave-particle duality or the Heisenberg uncertainty principle, and you feel pretty good about yourself. Like you got some equations under your belt, you're like, okay, this isn't so bad. It's a little weird, but it's not so bad. And then a couple years later, they tell you to forget all of that. And instead they teach you something else about quantum mechanics. They teach you the Schrodinger equation. And at first the Schrodinger equation doesn't make any sense at all. It's really weird and like how can this equation work? And you start to get used to the idea of probabilities and the use of the wave equation and all that. And then you graduate as an undergraduate and you feel like, okay, I think I understand quantum mechanics. And then you get into graduate school, and I remember my first quantum mechanics course in graduate school, and it opened with the professor saying, forget everything you know about quantum mechanics, we're gonna rebuild your knowledge. We are going to do it all over again. The way that quantum mechanics is taught to physicists doesn't focus on the meaning, doesn't focus on the interpretation, doesn't focus on what this means for reality. Instead, it just focuses on the equations and solving problems and getting a handle on it. As a physicist, you end up developing an intuition in quantum mechanics of how to use the mathematics and the formalism, but you never get taught the larger picture. And I think this is a major failing of physics education, because then when physicists go out into the world and start talking about quantum mechanics and working with journalists or the public to create videos about quantum mechanics,
primarily focused on observing
all we have as physicists is the math,
applies the laws of physics and chemistry
the formalism, the postulates, the equations, and we're not really taught or equipped with the larger picture of quantum mechanics. And so quantum mechanics becomes a confusing thing to talk about because the people talking about it are themselves confused. And I will admit to you up front, quantum mechanics confuses me. And I'm willing to bet that every single person in the world is confused by quantum mechanics. Even the founders of quantum theory themselves were confused by the very theory that they were developing. They were constantly arguing back and forth about what it meant, or what's real, what's not real, what does this mean, what does this not mean, what is important, what's not important, constantly arguing, and those arguments persist to the present day. So if you are confused
how is it expanding
by quantum mechanics,
cosmologists have similar schooling at astrophysicists.
It is confusing for everybody,
after having
even
that background
professional
in
physicists.
Cosmologists can also work with
quantum mechanics,
university
though,
labs and
has a very specific place in the larger tapestry of physics. I like to think of the different domains of physics as little kingdoms or little mafia turfs, little regions that they control. So we've got, say, Maxwell over here, and it's his turf, and that's the turf of electromagnetism, and we use his equations, his laws to describe how electricity and magnetism and light behave. And then we have Einstein over here and Newton over here to describe different aspects of gravity and so on. And so the quantum mechanics turf, the quantum mechanics realm, is the realm of subatomic particles. And it's important to keep that in mind. Like, where does quantum physics apply? It doesn't apply up here in the macroscopic world. It doesn't apply when I interact with you. It doesn't apply when I go to play, I guess. I don't play a lot, but like hypothetically, if I were to go play in a playground, like quantum physics doesn't apply. Quantum physics is the physics of the subatomic world. And the rules that we're able to generate in the subatomic world to describe the subatomic world are extremely weird. These rules are weird. So what does quantum physics teach us? Quantum physics teaches us that subatomic particles act as both waves and particles. So even using the word particles is a bit of a misnomer because sometimes they have particle-like properties and sometimes they have wave-like properties. Quantum physics teaches us that subatomic particles talk to each other potentially faster than the speed of light. They can influence each other. They become entangled with each other in a very, very non-intuitive way. Quantum physics teaches us that quantum particles, subatomic particles, can decide to randomly jump over impossibly high barriers. If I put an electron in a box and close the lid, in classical physics, that electron would stay in the box forever. But in quantum physics, the next time I go looking for that electron, it can just be on the other side of that box, just hanging out on the box, like waving at me, like how's it going, like no big deal. That doesn't make sense. Quantum physics teaches us that particles can exist in multiple states at the same time, that our intuitive link between a particle or an object and its state that means fixed in time and is localized right here and I can point at it, that doesn't make sense anymore. Quantum physics teaches us that particles don't necessarily have any measurable quantity we want, but we are fundamentally limited in the knowledge that we can acquire about their state. We can't know, say, their position and momentum to high precision at the same time. There's always going to be trade-offs. And of course, everyone's favorite, quantum physics tells us that subatomic particles don't always tell us everything about themselves. There is always going to be an aspect of the subatomic world that is permanently hidden from us. And it seems to be baked into nature. This is not a defect of experiment or our inability to be clever. It is just baked into reality. We aren't going to know everything we wish we could know about subatomic particles. This is all weird. This is just straight up weird. This doesn't make sense. We've been used to it for over 100 years, but that doesn't make it any easier to think about. And instead, that's why physicists, practicing physicists, even experts in quantum mechanics, use the mathematics so much, rely on the mathematics of quantum mechanics so much, because there isn't an intuitive picture that you can develop. Like other theories of physics, there's the math equations, which are critical, which are the physics. Physics is a mathematical description of nature. But if I have something like general relativity, yes, I have all these complicated equations of general relativity, but then I can sit here and describe it to you as the bending and warping of space-time and the influence of the bending of space-time on the motion of matter. That's pretty easy to visualize. That's pretty easy to think about. It's pretty easy to get an intuitive sense of how general relativity works just through the words. I don't have that option. Nobody has that option with quantum mechanics because I have a set of equations that describe the rules of the subatomic world, of how that world works under that kingdom, under that mafia turf. Those are the rules of that domain. But then when I go to try to use words to describe it, it all falls apart and nothing makes sense. So physicists rely on the mathematics, which ultimately physicists do across physics because that's literally what physics is. But in the case of quantum mechanics, there is no universally agreed upon interpretation. And all the interpretations of quantum mechanics have their shortcomings. So if you encounter a topic about quantum mechanics, I want you to take away two things from this video. One, quantum mechanics is just going to be confusing. If you look at it, yeah, we can take these statements at face value, like wave-particle duality and the Heisenberg uncertainty principle and all that. It doesn't make sense. It's hard to visualize. And two, if anyone walks up to you and says that they have an interpretation of quantum mechanics that works, that makes sense, that is a complete picture, that encapsulates all the equations and just makes logical sense, they are lying to you because all the interpretations of quantum mechanics fall short. They all have shortcomings because they are all trying to use words, English words or natural language words, to describe mathematics, and the mathematics themselves, the equation themselves, don't make sense. Thank you so much for watching. Please go to patreon.com/pmsutter. Be sure to like, share, and subscribe, and I'll see you next time.